Hello, this video covers some of the questions that are often asked in office hours regarding Unit 2, Module 4 homework. Okay, so this question is asking about potential energy states. So as we talked about in class, electronegativity is used to describe the stability of atoms, of their electrons. It's a stability scale. The higher the electronegativity, the more stable the electrons are. And we'll talk about what that stability leads to, which is partial negative charges or lack of them if they're unstable atoms. So in general, the smaller the atom, the more stable the atom. And the lower the potential energy of the electrons, because since the atom is smaller, the electrons are closer to the nucleus, and so we think of those electrons and that system, that atom, as being more stable because it has a lower potential energy. So if we look at the size here as we go down the column, these are the halides. So is the column right next to the noble gases. What we see is fluorine is the smallest. And since it's the smallest, it's the most stable. Has the highest electronegativity of the group, and therefore would have the lowest potential energy. Come down to iodine. It's the largest, so it's the least stable, meaning the electron, proton are the farthest apart. Has the lowest electronegativity, which also means it has the highest potential energy, right? So stability and potential energy, since potential energy is negative, we have to kind of consider that, right? So when we think about potential energy here, so it goes down. Remember, this is a negative quantity. It's a negative quantity. So the lower, right? The lower the potential energy, and we'll call this lowest. This is going to be the most stable. It's going to be the most stable the farther you go down. So the lower the potential energy, the more stable the system is, if we define zero there. So that's one of the aspects of the language in terms of describing negative numbers that you'll have to make sure that you practice working on. Right, so we get lots of questions on this one regarding ranking these molecules from most polar. This is a net polarity, right? So the net polarity of the molecule. And so let's do that. So the first thing we recognize that all these molecules, all three of them, have polar bonds. The most polar being the carbon-fluorine bond. But because there are four of them in a tetrahedron and they exactly cancel out, although there are four polar bonds, they exactly cancel. And that's going to be true for any CX4, any carbon atom that is attached to four identical atoms. They're all going to cancel. They have to be identical, right? They have to be identical. Something that would be polar would be CX3Y, right? Now they're not the same. But if they're all the same, CX4, then you expect all four to cancel in that tetrahedron environment. Okay, so all are nonpolar. CX4. Okay, so least polar here. Yeah. So now we have these polar nitrogen. So any central atom with a lone pair is going to be polar. Why? Because there's a lone pair, and so there's not a perfect symmetry here. So remember, most molecules are polar. The only molecules that aren't have these like symmetric, very symmetric structures. Well, there's a lone pair, so this is clearly polar. The nitrogen-fluorine bond is polarized. So the most polar would be the nitrogen-fluorine bond. It's the shortest, and it's got the biggest difference in energy. So when we go down, so anytime a central atom has a lone pair, it's always polar. Then as the bond polarity goes down, so now nitrogen-chlorine is less polar than nitrogen-fluorine. So these three contributions to the net dipole are now weakening. And so the least contribution is the nitrogen-bromine bond. It's still going to be the least polar bond, while the nitrogen-fluorine is going to be the strongest. So if we had to rank these in terms of like on a scale of what's most polar, what's least polar, we would pick NF3 to be the most polar because it has the 3 most polar bonds, and then it has the lone pair. And if we're just comparing that particular structure, we could rank these based just on the bond polarity alone. Okay, so which statements are true here? So the first one is all polar molecules must have one polar bond. Right? And that's fairly reasonable, given that there has to be some difference in energy between the in the bond, right? So there has to be at least one bond that's weaker than the others. And because of the difference in energy, where how electrons are spending around one atom versus another, that's what leads to the polarity. So at least one bond has to be polar. So all nonpolar molecules have nonpolar bonds. That is incorrect, as we've seen in class and we just talked about. With CF4, there are 4 very polar bonds, but they overall cancel, right? They contribute in opposite ways, and due to that, they cancel to leave a net effect of a nonpolar molecule. The higher the electronegativity of an atom, the more polar the atom is. Well, so electronegativity is really about bonding in bonding, and so we're talking about stability of an atom. So electronegativity tells you about the stability of an atom, but doesn't tell you about how polar an atom is. It tells you how polar a bond is. So C would be incorrect. And we get to D, which has the correct answer, which is the higher the electronegativity difference between 2 bonded atoms, the more polar the bond. And that's going to be true. So let's take a model. Let's look at a model here. So if X has lower electronegativity, means it's less stable, higher potential energy, and Y is more electronegative, then we would see an energy environment like this. And so what would happen is, as the electrons in the bond are going to spend more time around the more stable atom. And so by spending more time around Y takes on a partial negative charge because it's more stable, lower potential energy. X is less stable, higher potential energy. The electrons spend less time around it and take on a partial positive charge. So any atom that has a higher electronegativity takes on a partial negative charge. Least stable take on partial positive charges, right? So that's the origin of how the partial charges are assigned. Whichever atom's the most stable will have the partial negative charge on it. All right, that gives you that. So that gives us A and D as correct answers. Right, another question that comes up often in office hours is, well, how do we assign the partial charges when given a generic structure? So let's take a look at this one. So what we're going to do is we're going to recognize a couple things. First, we need an electronegativity scale that helps us. Okay, so what this means is that, and remember, in general, carbon-hydrogen bond are considered significantly close, that they don't really produce partial charges, or if they do, because of symmetry in all of these tetrahedral environments, they cancel, and so the net effect is the carbon-hydrogen bond is far less polar than we would expect. But carbon-oxygen bonds are definitely polar. And they're polarized in this way. All carbon-oxygen bonds are polarized this way. We get a partial positive charge on carbon, partial negative charge on oxygen, because oxygen is much smaller. It has a higher electron negativity. And so every time we see oxygens, we can pretty much write partial negatives around them. Any carbon attached to an oxygen will get a partial positive charge. So all the carbons and carbon hydrogens, we're just going to write 0 there because they're not attached to any polarizing, there's no polar bond in this area. When we look at the nitrogen, so carbon nitrogen is going to have the same story. Nitrogen is more electronegative, more stable than carbon. Nitrogen takes on a partial negative charge. Carbon that's attached to nitrogen takes on a partial positive charge. And then the nitrogen-hydrogen bond is also polarized, and so each of the hydrogens attached to nitrogen would also have a partial positive charge. So those would be how we would assign the partial charges on a molecule like this. All right, so this question comes up as often on exams and in the homework. All right, so let's take a look. What are we trying to do here? Well, what we're trying to do is show the correct net dipole for a three-dimensional functional group, right? There's a functional group, an amine that's attached to a phenyl group. And so what we want to, it's challenging. A lot of students don't want to call this polar because it looks like, all of these might cancel. Remember, this is partial plus our arrow, our bond dipole is partial plus the partial minus. And so that's going to be the nitrogens here and the hydrogens here. So we do that for 3 contributions, and now there isn't a 4th contribution because of the lone pair here. And so what we have to do is take a look at these renderings and say, okay, well, A and B are wrong because it's showing a partial plus at nitrogen instead of the hydrogen. So A and B are wrong right off the bat. And the question is, well, which one's correct, C or D? Well, to look at these, we have to look at the sum, right? The sum contribution. Remember, this is a trigonal pyramid, so it's not a planar structure. Each of these bonds are contributing in this pyramid like the edges of a pyramid. And so because of that, the net effect, right? The net effect, C, is the sum of this bond, and of this bond. So all 3 are contributing to this net dipole pointing through nitrogen, through its lone pair, making C correct. D is only showing 1 contribution, right, along the carbon-nitrogen bond. And so this is a bond dipole. D is a bond dipole. Is not including the contributions of nitrogen and hydrogen in the 2 NH bonds, which makes D incorrect because that is not a net dipole, what's shown in D. C is the one that shows that correctly. All right, so the final question we have is regarding PES, or what are called potential energy diagrams, or potential energy surfaces. So let's see how we interpret it. Well, first, blue is the partial positive, red is the partial negative. So we just kind of follow this. Looks like there's 6 symmetric partial pluses and partial minuses here. When the net result is that it's nonpolar, they sum to 0. 6 polar bonds, but they sum together to be nonpolar. When we look at B, there seems to be a clear bond net dipole here. You have a greenish blue at the bottom, all pointing to red on top. So we can assign this dipole B as polar. C has the same story, has this sort of reddish in. It's not symmetric. So remember, the key to whether a surface is describing something polar or nonpolar is it perfectly symmetric? So to be nonpolar, right, the main condition, nonpolar means completely symmetric. And so without the lack of symmetry, so this is not symmetric, this is symmetric. And so when we look at it, it's got to be nonpolar because of that symmetry. So that leads us to picking, and also keep in mind that red was partial minus and blue was partial plus. But since they're all at the same energy, right? They're all the same energy in D. It's a nonpolar molecule. Now, of course, our exams are in black and white, so you won't have to do this. The last question is much more like it. You won't have any PES surfaces on our test, but it is a nice visual representation of something that's polar, right? So polar bonds, net nonpolar, polar bonds, net polar, right? And that's true for both of these. And then in D, nonpolar with nonpolar bonds, right? Because of the total symmetry, lack of charge distribution. All right, so those answer the questions that are frequently asked in office hours. And if you have any other ones, please screenshot them and email it to me.